Yeah, a little geology then. Not very much, but a little. Okay, so we've obviously identified pretty much the rock that we're sitting on, okay? So let's back up a little bit before we name it, and let's look at the colorations and stuff. Can we see crystals in this rock?
Yes.
Yes. So that would make it what texture? Coarse or fine grained? Coarse grained, right. So all you need to do is just circle that. Okay. Okay, so we can see crystals. We see that there's different colors of the crystals. We have dark colored minerals on the basis of being black. We have some light colored minerals, possibly being white. It's sort of hard to tell if any of the minerals are pink because we have a lot of oxidation in the area. And the oxidation is due to the fact of the large amount of iron or hematite that's in the area. And so that gives the rocks here their rusty red color. But they're also black in color too. And that's mostly due to another type of oxidation that occurs based on exposure to the sun. For those of you that were on Fred's Telegraph Pass field trip with me, or Bankers or Earls, when you were in Telegraph Pass, you noticed that the rocks were very dark colored there. And then when you went out to Fortuna Wash, we saw that some of the rocks on the left were light colored in comparison to the dark color. So they hadn't been exposed to the sun as much. Okay, so we have some dark colors, we have some light colors, we also see some sparkles as a result of the sun shining on them. So what are some of the names that we could give this mineral composition of this particular rock? What would the white colored rock probably be? Not yet, but hold that thought. Whoever said feldspar. Okay.
Quartz.
Quartz, right. Most common white mineral that we have on Earth. Quartz would be one of our minerals. Now, the other lighter colored mineral, which may also be pink, would be...
Feldspar.
Yeah, one of the feldspars. Which feldspar is it? Orthoclase or plagioclase?
Ortho.
Ortho, right. Okay. And then what would our sparkly mineral be here?
Muscovite?
It could be the muscovite, and you passed lots of muscovite on the ground as you were walking in. I mean, it was all over the ground because there's a little vein of it that's up a little bit higher. It could be the muscovite. What would be the black sparkle? Biotite, right. So it's hard to tell whether it's the muscovite or the biotite, okay? So it could be either one because we do know there's a large muscovite deposit, okay? Now, since we have the quartz, the feldspar, and the micas, then the name of this rock then would be...
Let's put them all together.
The name of this rock would be... Nice, right, exactly. That's right. And there might be some schist, okay? In fact, if we look over in this area right here, this is more schistic than it is gneissic. And then if we look over here, this is more like schist than the gneiss. And the reason being is because of the structure that I'm sitting on, okay? The age of our gneiss comes in at approximately 1.6 billion years old. BYO, okay? Not bring your own. Billion years old. So it's extremely old. We also saw very, very old gneiss when we were at Telegraph Pass, okay? So if we have gneiss here and we have gneiss way over there where we were, would that be regional metamorphism, contact metamorphism, or dynamic metamorphism? Regional, right, because it's covering a large expanse of area. It's all over. So we have regional metamorphism occurring. Now, as I said, we have sort of a difference between the gneiss and the schist. Notice also, too, the angle at which the lines are, or the foliation is. Well, actually, I just gave you an answer, didn't I? Foliated texture. Sorry about that. You're welcome. Notice that it's almost at 90 degrees. Because of this angle, this creates a weakness in between the layers. And so that weakness allows for erosion to take place. But the other thing that causes the erosion to take place is the structure that I'm sitting on, which is of a totally different rock type. But we'll get to that in a minute, okay? So here we have this almost vertical foliation occurring of the layers. We see that we have a changing from the gneiss to a schist, okay? And as a result, this tells us that there's been a change of heat or a change of pressure. Bless you. Thank you. There you go. You're good for the whole field trip. How's that? Woo! You can climb up the side of the cliff and you're good. God's not going to let you fall. You've been blessed by everybody.
Thanks to you.
So, what we have here is another structure that's considered to be igneous rock, okay? And I'm going to move off of it so you can see how far back it extends. It goes all the way back there. And then it's been eroded away here, but then it also extends up the side of that slope there. So it's an extremely long igneous intrusion here. Of the 5 different types of intrusions, batholith, laccolith, stock, sill, and dike, which one would it be?
Batholith.
No, you lie. You flunk.
Dike.
It's a dike, right. Okay, so here we have a dike that's of a totally different kind of rock. It's an igneous rock rather than metamorphic. It is quite large. It extends all the way up to the side here and goes all the way over to here. And then you can see how wide it is up there on the slope. So it's a very, very large crack that got filled in by magma. While the whole magma body of metamorphic gneiss was underground. Okay? So, excuse me. As a result, we have another type of metamorphism that has occurred. If we look, we can see that the crystals are very, very noticeable. We have large gray crystals here. We have white crystals here. But yet, as we get to the edges of the dike, the crystals become very, very small. Instead of being coarse-grained, they almost get to a fine-grained texture. What kind of metamorphism is that considered to be?
I'll just quit cooling. Huh?
We already said we had regional. What are the other 2 types? Contact metamorphism, right. And that's why we have the schist. Because the heat from this dike actually recooked the gneiss and changed its composition from being gneiss into being schist. And so right along the edges here, we have schist. Right along the edges here, we have schist as a result of this recooking of the country rock. Now, the dike is also a really good indication of why we have a lot of prospecting out here, okay? Where you have these kinds of quartz-type dikes, you're probably going to find gold, silver, or copper. Because this magma, sometimes in its recipe, has dissolved minerals in it that are usually highly contented with water. And gold, silver, and copper have a tendency to be these highly dissolved minerals. And so when you're walking around and you see holes in the sides that look like little starts of caves, that's where somebody came out here with a pickaxe and a chisel and thought, I might find some gold out here. When we drove in, there was that sign that said Broken Dreams. Well, that sort of sums it up for whoever's prospecting claim this is. They thought they were going to dream of being rich with gold, and guess what? But there are people that come out here and work the rock and work the dirt looking for those small little flecks of gold, wherever they may be, okay? And so what we end up finding happening here is a lot of prospecting going on. Now, this particular dike, made up of, obviously, the white for quartz, okay, as far as one of the minerals. And this is going to be where it says 3B, pegmatite. Okay, so we're on page 3, about a third of the way down. Okay, so quartz is going to be one. We have the gray mineral. What feldspar do we think that might be? We had the orthoclase, so plagioclase. We could have plagioclase in here. Okay, and then no, you're right here.
This is 3 now? 3.
Yeah, we're at 3B.
Oh.
Oh. Okay.
Okay.
Yeah, there's an A and a B to this stop.
What course is this? Fine grain?
This is coarse grain.
Coarse grain?
Yeah, you can see the big gray crystals in it.
So the first one was coarse grain too, right?
Yes. Okay.
So the mineral composition on
Okay,
this
the
one.
white is going to be your quartz. We just said that the gray is probably the plagioclase. And you can't see it in the space here, but if you look back here, we have the silver sparkle, which would be which mica? The silver one. The black one was the biotite, so the muscatite, right? Muscovite. There we go, muscovite.
Did you say feldspar?
Yes, the plagioclase.
Oh.
Okay, and so the rock name of this is what it says right at the top. This is pegmatite. And unfortunately, it's really hard to get small samples of pegmatite, so it's not in your actual rock box. Okay. Okay. Now, we have, this comes in at an age of approximately 70 million years ago. So, the metamorphic gneiss was underground for a very, very long time before the pegmatite found the cracks to ooze into, and then the whole metamorphic body then oozed its way up in terms of through faulting and stuff. Now, this dike being here, this dike has also helped to create the weakness that has allowed for this little wash to form, or this erosional area to form. Now, if I were to ask you which is older, the gneiss or the pegmatite, what would you say? The gneiss, right. And that's because of the principle of cross-cutting relationships. And if you're in chapter 17 or have had chapter 17 yet on geologic time, that's one of your 7 major principles, cross-cutting relationships. And what it says is whatever cuts through a rock is going to be younger than the rock that it cuts through. We also have the presence of another structure that also tells us that the dike is younger, and that's this structure right here. Here, inside of the pegmatite dike, we find a piece of the gneiss. Ooh, how did that get there? Well, it got there through a process called stoping. S-T-O-P-I-N-G. Not stopping, stoping. And this is where you have a crack that gets filled in by new magma. And as that magma's coming